Okay, so we're happy to have Bartosz Wcisło to talk on saturation properties for propositionally sound satisfaction classes. And many long-time speaker at MOPA, so we're very happy to have you back, Bartosz.
Yes,
Go ahead.
yes. Likewise, it's really always a great pleasure to speak at this seminar. So I'm very grateful for the invitation. And it's really a great pleasure to see so many familiar faces, and I think it's even more pleasure to see some new faces. Okay, the title sounds somewhat technical. I guess the talk will be also a bit more technical than I usually try to aim for, but let's try to go for it together. Okay, so what's our problem? So actually, the talk is motivated by one of the topics which are of my central interest. So the Tarski boundary problem, and the problem asks. Okay, you might have. By the way, sorry. Please remind me. The MOPA is always an hour, right?
Yeah, roughly we
Sure.
can go over by 10, 15
I
minutes.
just had this slight peak of panic that maybe I somehow confused it, but sorry. So the talk is motivated by the Tarski boundary problem. The problem asks, what principles can you assume about compositional truth so that it becomes non-conservative? Okay, so probably from the description, only those of you who've already seen this problem discussed could understand it, but let me maybe add some more background and then become quite clear. The result itself can be phrased that actually is of the nature of like pure model theory. So this is something where where motivation comes from proof theory, but actually the result will be purely about models. And I will try to, at the very end, say a few words of how the result originated and why, and whether it has some impact on the original motivational questions. I think that the answer might be yes, but let's postpone this until discussion. Okay, so now about the first phrase. So what are the main actors of today's talk and why we care? What is Tarski boundary problem about? So for some of you, this definition will be probably like seeing a very old friend, but for some of you maybe new, so let's go for it. The very context of this research is analysis of extensions of a theory CT minus. What the CT minus is? CT minus stands for compositional truth, and this is a axiomatic treatment or axiomatization of compositional Tarski conditions for a truth predicate applied to arithmetical sentences. So what are the axioms? Okay, now it gets always nasty to say. It's very easy actually to understand, but much harder to understand when you read it. Once you read it, so think of it simply like if you haven't seen it. We want to say things. Okay, maybe let me write here. Let's say we want to say things like an equality between terms is true if and only if. Well, essentially, s equals t, but they have some values. So you put some value function here. You want to say things like a conjunction is true if and only if both of the conjuncts are. But now the point is that you want to actually state it axiomatically. As quantification over sentences doesn't make sense, but it does make sense to speak of codes of sentences, right? So of the formal objects, which are formally sentences in the model. And again, like in the model of PA, it makes sense to quantify over terms in the sense of PA. So you see, if you take any two codes of terms, so possibly in a non-standard model, this could be non-standard objects, which simply, if you unwrap them and unwrap the definitions of what a term or a formula is from your first Gödel textbook, you will see that those objects are terms. You can likewise compute formally their arithmetical values using recursive definition for a value, and you say that If you have arithmetical terms, the equality holds if the value matches, and likewise for the other axioms. So negation, this truth is classical, negation holds if and only if the negated sentence doesn't. The disjunction holds if and only if the disjunction holds. I got it wrong, so we're using disjunctions rather than conjunctions. An existential statement, you have to think a bit, but it's doable, right? What existential statement says? Well, it's witnessed by a numeral. So you say there exists an object phi is true if and only if for some numeral x substituted for phi, the sentence you will get is going to be true. So this is slightly technical and won't need it just to actually state what I'm saying. When I'm writing CT minus, I always assume this axiom, which is so-called regularity, which says if you give me two sequences of closed terms, possibly of non-standard length, possibly of non-standard terms, such that their values match pointwise, then you can freely substitute them salva veritate. Sorry, I think I went over to the slide very slowly. If there are any questions, then please do ask them, because that's like the rest of the talk will completely make no sense if there is any confusion as to this point. But I hope that it's not needed. Okay, let's go. Let's continue. If there are any questions, like please tell me to go back.
Bartek, so let me ask. So number 5.
Yes.
So this usually has not been included in CT minus.
No, I mean, like, okay, so yes, I mean that's an awkward thing because it's normally not included. I kind of I would say I campaign for including it standardly in the definition of CT minus. Well, first of all, because I was saying that there are just so close connections to the theory of satisfaction classes, but this is actually, without this axiom, it's actually not known. So without any induction and without this kind of axiom, connection with satisfaction classes gets messy for weird reasons. And the connection, and moreover, there are a couple of results, including the theorem on the next slide, or in two next slides, won't be so neat if I don't include this axiom, because then sometimes I would have to include it, sometimes I wouldn't, but some other close statements would get true. So I think without this axiom, it's just
right. So in other words, could you just say, in general, we are really very interested in pathologies, the truth predicates or satisfaction relations that are sort of violate certain principles that I think that they should satisfy. But if you eliminate 5, then the pathology goes too far, or may go too far.
Yes, that's it's not only it goes too far, but I would say it goes too far in uninteresting ways. So there is a body of interesting results about how other pathologies connect one another. And with this pathology, it just seems to stick out in a boring direction. So, but yeah, I'm not. Yeah. So officially, I'm including it in this talk. I included in the papers where I have the final say over this. Whenever I have, but yeah, you're right. It's not standardly included. Okay, let me continue. Okay, let me erase it. So if you minus stands for lack of induction, if you add induction, you erase minus, it's CT. Okay, so I said we try to understand which extensions of the compositional theory of truth are strong. So the theory itself is weak. This is the classical theorem of Klotowski-Lachlan rephrased as a proof-theoretic result. It simply says that CT minus is conservative over P. If you work with full induction, you can actually, so if you add full induction here, so if you work with CT, you can actually formalize a natural argument for soundness of, say, sequent calculus or natural deduction, and show that whenever you prove something by induction on the length of the proof, whenever you prove something from true premises, the conclusion is true, which says that probable sentences are true, which means that you cannot prove 0 equals 1, and you get non-conservativeness of a PA, right? You prove consistency from CT, you prove reflection, you can iterate reflection. Actually, you can iterate reflection epsilon not many times. So it's not a conservative extension. Okay. So now the question is this. More specifically, like to stress on this point, CT proves in particular the following principle, which we'll refer to, of global reflection, which says if you take a sentence which is arithmetical and probable in PA, then it's true. So if PA proves something, this is true in the sense of truth predicate. Okay, so the question now asks, as Roman already said, essentially study of CT, extension of CT minus is study of how strong it, whether it has a strong statement to eliminate certain pathologies. So the ultimate elimination of pathologies is adding full induction. You can just, probably if you think that some class of sentences just should be intuitively rendered true, some class of non-standard sentences, then most likely a reason for it, barring some maybe more exotic examples, but probably a reason is induction. So like when you have induction, you probably expect to have no genuine pathologies. On the other hand, if you have just compositionality, just conservative. So we ask what other nice things we can say about predicate, which will make it still conservative, and then when it becomes non-conservative, when it becomes strong. And I'm stating this principle of global reflection because it's something that obviously makes CT minus strong. So CT minus with global reflection obviously is not conservative because you can prove that, say, 0 equals 1 is not so 0 equals 1 is not true, hence it's not provable by contraposition. So you proved consistency of PA, actually you proved reflection over PA, uniform reflection. Okay, let's go further. So as I said in the beginning, there is the Tarski boundary program. It tries to see. The Tarski boundary program asks which of the natural extensions of CT minus are conservative, and actually, it sounds like a hopelessly zoological question, but it's not. So actually, there seems to be a very clear and crisp distinction. So following natural principles turned out to be equivalent, just equivalent to this global reflection. So for example, delta zero induction. First order reflection just for reflection just for logic. So if you say that something is provable in logic, in pure logic from true premises, it's true. This is also equivalent to reflection over PA. First order soundness, which says if something is just provable in first order logic, if it's first order validity, then it's true. Propositional reflection, which says if you prove something from true premises in pure propositional calculus, but applied to arithmetical sentences. So for example, from many premises, you can form their big disjunction or conjunction, right? This is what propositional reasoning allows you for. Then it's true. Just a tiny bit of this propositional reflection, disjunctive correctness. So if you give me a big disjunction, like with C many disjuncts where C is passively non-standard, then it's true if and only if it has a true disjunct. So it's a tiny bit of propositional reflection. This is also equivalent to global reflection. Disjunctive elimination. So if DC out, so if you take such a big disjunction with non-standardly many disjuncts, it is true. If it is true, then it has true disjunct. So a general emerging phenomenon is that if you give me a natural extension of CT minus where natural is not specified in any pleasant manner here, it's either conservative or exactly equivalent to CT minus plus global reflection. So thus far, we have found no natural counterexample. Like by natural, I mean a counterexample which was not handcrafted specifically to not fall into any of these two categories. And let me also stress that the proofs here, it's not just a repetition and elaboration on the same proof time and again. Actually, all the equivalences here use very different proofs. So each time you use different methods, maybe different methods a bit too far, but each time you use a genuinely different argument. So there seems to be like no master argument for which would prove all the equivalences in a very uniform fashion.
So
all of them were, yes.
So because it looks very interesting what you just said. So it also applies to Cieśliński's results, the pure sentential logic and this, all the three, are they also each of those uses a different method?
Yes, surprisingly, yes. I mean, like first order reflection maybe is something that is maybe like proposition rather than a theorem. But actually, propositional reflection was a very non-trivial observation, and it went through first through equivalence with delta zero induction, but then it used this Gapi argument of Kotlarski that delta zero induction proves global reflection. And first order soundness was a problem, and then Cieśliński, a couple of years later, found a different proof that first order soundness also. Actually, this was a candidate for a principle that might be in the middle between global reflection and just conservative theories.
And is this all in Cieśliński's book? Or was it done later?
No, it will be in the forthcoming book. So we're writing a new book. Actually, maybe the timing is not very good, but because hopefully, okay, so like, because hopefully, like the pesky remaining open problem will be no more open. But let us see. So there are some. Okay, so there are more principles that are on this list, but I wanted just to give you the gist of it. We have more conservativity results and more results of equivalence to this global reflection. And this talk is about one of the most pesky remaining results. It's propositional sums. So let's go one slide back. So propositional reflection says, from true premises in propositional calculus, you can only infer true conclusions. First order reflection says, from true premises in first order logic, you can only get true conclusions. First order soundness says from like true validities of first order logic are true. And propositional soundness likewise says tautologies of propositional logic are true. So those are tautologies in the language of these are tautologies in the language of arithmetic. So for instance, CT minus plus propositional soundness proves that for all I, and now this is really quantified, the sentence maybe for all C, for all C, the sentence, the conjunction I less than C, say I equals I, or I is not equal I, this is true. Right? So this is an arithmetical statement. This is numerals, of course, so for it to be a legal statement. So this is an arithmetical statement, but it's also a propositional tautology.
And will you say how the parentheses are distributed?
Anyway. Okay, so actually if you have propositional soundness, it doesn't matter. Because under propositional soundness, you can show that
I see.
That conjunction is associative, right? So you can show by, and actually, associative, it's not by induction, but for any conjunction, you can prove like generalized associativity. That if you have two conjunctions parenthesized no matter how, then it's equivalent. So for each of them, it will prove the same. By the way, when I write, because it doesn't matter here, but it might matter in the future. So whenever I write this, I mean, and I don't make any precise statement about this, I parenthesize to the lowest index. So it's parenthesized linearly to the lowest index, which sometimes might matter, but hopefully not in a very brutal way. It does matter in other papers. Okay, so we're asking, I'm now clearing the picture. Okay, so we're asking whether this is conservative or not. In other words, if you say any propositional tautology is true, is it conservative or not? And we've been attacking this problem for years. I'm going to discuss some model theoretic partial results, which seems to suggest, well, it seems to suggest in a soft way that it's not conservative, that it's also global reflection. And in more concrete manner, they suggest that known methods for showing conservativity, the main method we have, will not be suitable for attacking this problem. That if it's conservative, the proof will evade the methods we use. Okay, so one of the basic, so not about the model theoretic results. So one of the basic facts about models of compositional theories of truth is a theorem of Lachlan, stated, of course, originally for satisfaction classes. It says, if you give me a non-standard model, then if you give me a non-standard model of a compositional truth theory, then the arithmetical part of the model is recursively saturated. Which hopefully, for those of you who haven't heard of it, comes as a shock, because, like compositional truth is something so local. Like, it seems that you should be able to just add it to any model just by, like the way you pick ultra filters. Essentially, you just have to decide every sentence, is it true or false, and you're good. You have to do this like in a with barely any complications, with barely any effort, just to keep some local conditions. But no, it turns out that the local conditions are pesky and difficult. And then we'll actually make use of the proof of this theorem. In a paper with Roman, we've rephrased this in much more general framework. The proof, not the theorem. And then this general framework, in the study of truth theories, it seems to be kind of like one of the main tools, because here and now, here and again, time and again, now and then, it spills off nice, small results, which maybe hopefully will bring some clarity to the final problem. Okay, so actually the result which will follow much more closely, this will be the direct analog, is Smith's non-standard overload spill. So this might be less known, so let me go for it. So take a model of compositional truth, take arithmetical sentence in the sense of M, and suppose that the sentence holds of any standard number. Then it spills over to a non-standard number. Right? So this already seems very surprising. A non-standard sentence, like for standard sentences, this is true, this is clear. This is a model of PA, you have induction. You don't have, in general, induction from non-standard sentences. You can add it as an axiom, but it's not automatic. But it turns out that even though you don't have induction, you have like a bit of saturation, which gives you overspill. Okay, and we will prove a very related result. So the lemma says, well, maybe I could call it theorem. So suppose you have a, yeah, I mean, lemma maybe is an understatement. It's not. This will be the main result of the talk. So, so let's call it theorem. So take a model of CT minus with propositional sumness. Give me a coded sequence of arithmetical sentences such that first omega of many of them are true in the sense of the truth predicate. So then there is a whole non-standard initial segment such that all of them are true. So what's for comparison is this. For Smith's theorem, you had one sentence and you vary the numbers. You spill over with the same formula. You spill over the numbers about which this formula speaks. And here you have a non-standard, and here you have a whole sequence of sentences. I don't know, hopefully clear. So it's a highly non-uniform version of overspill. You spill over the whole sequence of form.
I have a question.
Okay,
When
okay,
you say
great.
When there exists D, do you mean that D is non-standard?
Yes, of course. Thank you. Of course. Yes. So another way, like if you know that a sequence of form of sentences is true up to omega, then it spills over to here. And maybe now a tiny remark. So why it suggests that something strong is going on. We could think of this as as like with normal overspill as somehow related to induction principle. So we could think of this kind of induction, which says for all I less than C, truth of phi I implies truth of phi I plus 1, and phi 0 is true. Then for all I less than C, T of phi I, right? So for all C, for all phi I, for all C, for all sequences of arithmetical sentences, if the truth is progressive and holds at 0, then it holds for the whole sequence. So this principle, again, it can be shown to be just equivalent to global reflection. Even though in general context, for a general predicate, it's not equivalent to, say, delta zero induction. It's a very weak form of induction normally in the general arithmetical context, but in this context, in the context of truth theory, this is again delta zero. This is again full delta zero induction. So so this form of induction, it might seem very weak, but actually it's very close. It's tiny bit of distance from the actual full global reflection. So it's actually a tiny bit of distance from showing that propositional soundness is true. Okay, let me go further.
So can I ask a question?
Yes, sure.
I don't quite know how to phrase this, but it seems sure. I assume there's content here that will explain why I'm misunderstanding something. But you have a coded sequence of sentences.
Mhm.
Could you not form a formula that would just be that would just kind of say phi of x is the xth element, right? The xth element of this sequence phi I.
So
And
you're
then
asking yes. So we're basically asking whether this could be derived as a corollary to non-standard overspeed, right?
Yes, exactly. I'm trying to
No.
understand why this is
No,
not directly
it
that.
no, it cannot be. I mean, like, it's not the, like, I can give you a reason why it's why I know this doesn't follow. It doesn't follow because, for instance, I was hoping to say this in the corollary section, but let me maybe this is actually a good moment, I think. So notice, for example, as one is a simple corollary, an example of what happens. So consider the formulae, for example, for formula. There exists x such that x equals x. There exists, or even, sorry, for all x. It's not very important difference, but let's make it like this. For all x, for all y, x equals x and y equals y. And actually, I should have indexed it, right? For all x1, x2, x3, the conjunction xi equals xi, right? And so on and so forth until I get for all x1, for all xc, conjunction of I less than c, xi equals xi is true. So far, so good? So from the propositional soundness principle, it follows that for some non-standard c and every j below c, this sentence will be true. Now, in general, we can easily arrange using an Ayat-Fisher construction that you'll have that the only initial, but actually you could even arrange that for all simply all sentences starting. You can be very pathological and simply arrange that class of compositional truth in which all sentences starting with non-standard block are false. Right? Like easily just stick it for the construction.
Right.
Right. So if you in Ayat-Fisher, you just pick any sentence. So you can arrange a very pathological class like this, in which like there is no completely correctness with respect to blocks of quantifiers. And yet, the fact that you have tautologies, propositional tautologies, allows you to show that at least some sentences, at least some first order validities starting with blocks of quantifiers will be true. Which therefore is completely beyond the scope of Lachlan's theorem or Smith's theorem.
Right, Bartek, but a follow-up, but that model could be a model of propositional soundness?
No, in particular, the corollary is not.
Right,
Which,
because what I was thinking of asking that you say that this is a form of saturation, a certain weak form of saturation. If MT is a recursively saturated pair, then it satisfies the conclusion without any assumption.
Yes, precisely. Yes.
But how about those constructing models of propositional soundness, say, in which omega is definable? I guess you can make one like that as maybe from an Ayat-Fisher, maybe it follows somehow. But it says that whenever the lemma seems to be saying that maybe you can define omega somehow, but not in this particular form. That's the content of the lemma.
Yes, precisely. Yes.
But is so you looked at some other forms of perhaps defining omega that are banned by this assumption, or not necessarily?
Well, that's complicated. One general reason why it can define omega in some way is for like general PA reasons. So because of course propositional soundness follows from delta zero induction, so you can just look at models with an extra predicate delta zero induction in which omega is definable. So we can do this.
All right.
But then of course the interesting question is now whether you can define omega in delta zero manner, and then this is precisely something I would be super happy to push further, but I can.
I have a vague recollection, maybe Laurie remembers, that Kostas Dimitrakopoulos has this paper where he actually studies this form of saturation that's really essentially models of omega overspill. And there are some for fragments. So it might be some interesting, so there might be some interesting examples that maybe you can get from the results there, but I don't remember what those results are. I'll look it up.
Okay, that sounds actually very relevant and very promising. Yes. Thank you. Thank you for this comment. Okay, I think I have to is it clear, Atar, is it clear? Like what's I know that it looks very similar to
Yeah, so I mean, I guess certainly your corollary. I follow that. That makes sense. I I need to think for a little bit about what it goes wrong with trying to apply.
yeah, I mean, but
I think it's some syntactic thing of trying to define
yes,
this
I mean, like
very fastly growing complexity formula.
like precisely just this thing when you try to write it down, it turns out that that you can't do it, right? That you like
Yep. Yeah. All right, great.
There's no like the deep reason why you can't, of course, is this, but there is no.
Good.
Okay, let's go further. Let me raise the discussion. Sorry. Oh yes. So okay, so now about the technical part. So I'll try to go a bit into the proof. It will be necessarily a bit faster than I would love to, but let me try. So this will be okay. So crucially, this uses disjunction of stopping condition. What are these? This is certain propositional construction. You from a sequence alpha and beta of sentences, you construct the following sentences. You define it backwards. So maybe let's see what it would look like for C equals 3 or something. So what you're saying is this: alpha so what you're saying is this. So it's either alpha 0 holds and beta 0 holds, or alpha 0 doesn't hold, and then I'm opening a new parenthesis. Alpha 0 fails, and then either alpha 1 holds and beta 1 holds, or alpha 1 fails, and then either alpha 2 and beta 2 holds, or and so on and so forth. And at the end of the day, you say, or alpha n minus 1 fails, alpha c minus 1 fails, let's say, and alpha c and beta c. Okay, complicated. How I think of it? I think of it as a set of instructions. I think of it as a set of instructions. So you have some condition alpha, which says you were to stop checking, at which stage you stop checking the truth of the formula, and then you check it by checking whether the condition beta holds. So maybe you have to stop checking at the level of a 0, then beta 0. Then your formula is equivalent to beta 0. Or maybe you have to stop checking at the stage alpha 1, and then formula beta 1 is, and then you check whether formula beta 1 holds. In the real world, so in other words, if the induction holds, this is just equivalent to saying either alpha 0 and beta 0, or not alpha 0 and alpha 1 and beta 1, or not alpha 0, not alpha 1, but alpha 2 and then beta 2, and so on. I'm going further. So if you don't, it's not very important what those formulas precisely are, but I decided that maybe it will be useful to say. What I do with them is this. There are two lemmas here. First of all, you take a model, you take an arbitrary non-standard element. This is now a model of pure compositional truth. If you didn't understand what this junction, what this construction is, that's not very important. The lemma is important. So you give me two sequences of arithmetical sentences in the sense of the model. And now suppose that for some external reason you know that that there exists K such that T alpha K holds, and in fact this K is standard. So you have some sequence of sentence alpha in the sense of the model. And in fact, you know, for external reason, that the first sentence, which in this sequence that happens to be true, will be standard. Then this whole complicated formula, even though truth predicate in general knows very little about propositional logic and pure, just assuming compositionality. So just from compositionality, you can cook up a whole sentence in an arithmetical way. So not using this external knowledge. This is a perfectly uniform construction in alpha and beta, such that it will precisely recognize this K, and it will test only beta K for truth. Uniformly, so the construction doesn't depend on any assumptions of the beta K or alpha K. The construction is uniform, but the way it behaves will precisely recognize this K. And the second lemma we'll use is the Frank lemma, which says it's easier. Take a model of PA, take a standard element. Suppose that you have certain rank function from a non-standard segment into some well ordering. Suppose that this function is almost monotone. So either each element is either bigger than the previous one, each value is bigger than the previous one, unless it's already maximal. And the conclusion is then you hit a maximal element. Well, I should have said well ordering with a maximal element. Right, so if you have a function that is locally monotone, then actually it hits the maximum. The lemma says for any two sequences of sentences, you can, in a uniform way, recognize whether the first sentence in a sequence, whether, in a way, which of the sentences of the sequence which one is the first true sentence, provided it's standard, it's a standard index. Yeah, as a warrant, it's a bit too technical, maybe.
But
Sure.
mostly, so all those A's are below C. The condition is also
Yes,
below.
yes. All the A's are below C, yes. So you're coloring segment with some ranks, and the ranks are kind of locally growing. Then this means you will actually hit the maximum. And actually, I can show you will hit maximum quite often. Okay. Now towards the proof of the main result of this overspeed result. So consider the following rank. So this is precisely a function of the form about which the rank lemma says. This will be certain rank. So first of all, if phi is simply false, then you put rank equals 0. This is as bad as it gets. If it holds, well, Yeah, I mean, with prefix over result, I'm assuming you have fixed your sequence phi I already. Sorry, that should be said. So I'm looking at how many of the phi i's I prove in propositional logic. What's the biggest segment such that I prove in the propositional logic? If the segment is standard, then I fix the k to be essentially the length of this segment. We're off by one, but this doesn't matter very much. Right, so look how much of the sequence phi I can prove. So if it's not zero and if it's not k standard, what it means? It means this is a true sentence, which proves all the standard sentences phi I in propositional logic. Then this is a good sentence, you put rank equals omega. Okay, if you look at rank lemma, what we need to check, what's enough is that I find a sequence of sentences such that the rank locally grows. Right? If I find a sequence gamma such that the rank is locally better and better, then by rank lemma, I will hit omega somewhere. Whenever I hit omega, this means this is a true sentence which proves in propositional logic all the phi i's for I standard, which means, in other words, that by overspill it proves phi I for I less than D for some non-standard D. So it's a true sentence which proves a large initial segments of phi I in propositional logic. So by propositional soundness, if that sentence is true, then actually all those phi i's have to be true. This will be on the next slide. Okay, so now I have to check some things. I have to check that I can actually express with a sentence that the sentence phi has rank at least I, but this can be done. And yeah, what I say is basically this. I know we're going fast, but that's the eternal curse of all the talks, that it always goes way slower than anyone sane would expect. So you can say that a sentence C has rank at most K. Simply say either not C or it got compiled where it should be, the indices should be not like an operator, sorry. Either it's C or it proves, or this is not tautology. So either this doesn't hold or this is not tautology. I can say it. And when you compile what it says the rank of C is at most I. On the other hand, let beta I be conjunction of the first I sentence from the sequence phi. So this beta I is a sentence that canonically has rank at least I plus 1. And then you define the sequence gamma I by induction in the following manner. So at the stage I plus 1, you essentially, this is the stopping condition. You look what if there is K standard such that gamma I has rank K, and if it does, then you put gamma I plus 1 equivalent to this beta K, to this beta K. So you make gamma I plus 1 in this manner a sentence canonically higher rank, which means the sequence gamma I can only grow in rank, like locally it grows. From I to I plus 1, gamma I plus 1 always has higher rank than gamma I, unless it's already of infinite rank. Okay, we're almost done. I know this part was kind of messy. someday I figure out how to convey it more clearly. But let me go now to the conclusion. So we conclude that there is an A such that sentence, this is type of gamma A, has rank omega. So there exists A, what gamma A having rank omega means. There exists A such that gamma A, first of all, is true in the sense of true predicate, and it entails quite a big disjunction. So a non-standard disjunction for some non-standard D. So since this is true in the entails disjunction, we know that tautologies are true, which means that this implication is true by compositional conditions. The conclusion is true, which means that this big conjunction is true. The big conjunction being true, again, using propositional soundness, means each of the conjuncts is, which proves the theorem. Okay, now a bit of some tiny remarks, some tiny ending remarks, concluding remarks. So first of all, this theorem can be lived to a uniform version. So you have a single C such that for any coded sequence, you have an overspill up to C. This kind of induction of this kind of overspill up to C. There is a sketch of the proof, but this is something I decided to skip. Right, so you can make all the sentences hit the induction for the sentences. The sequential induction holds up to the same point in the model. Okay,
but so you're skipping the proof, which is fine, which is definitely fine at this time. But this is a very interesting result in a sense, because while the C is somewhere in the model, right, and then how high it is in the model perhaps says something about the model. That if it makes any sense, you know.
Yeah. But okay, so still the hope is that maybe this is really for any C, right? For all we know, right. Propositional soundness could simply prove that as your induction, right? So and you know,
I see. So then it would be compatible with this sort of version of the I see. Because it's kind of unusual result.
Yes. You know, I was actually hoping that for some like general Fisserian reasons, this result could be actually lifted to the result for any C. Because this is on the next slide, right? So what conclusions we have about the status of propositional soundness? So there was another early result. Let me just mention it quickly. There we have an axiom of quantifier-free correctness. It says truth predicate agrees with the usual arithmetical truth predicate whenever you give me a sentence that's a Boolean combination of the equalities and non-equalities of terms, of closed terms. So this principle, truth behaves in the only way possible arithmetically on quantifier-free sentences. So if you say this, in itself, it's conservative over PA. However, if you add it to this propositional soundness, it gives you global reflection. So we're this tiny bit away from global reflection. This already shows that Enayat-Visser methods, which are standard for showing conservativeness, for those that this for cognoscendi, probably cannot hold, because this can be arranged, this quantifier-free correctness can be arranged locally and very easily, and by Enayat-Visser methods, they combine very well. So it's very unlikely that you could prove in a standard fashion that propositional soundness is conservative. However, it could be hoped we can construct it like in a manual way, because you can also use Enayat-Visser methods to obtain those models in which every non-standard block of quantifiers is true, every non-standard block of quantifiers is a false sentence. You can pick a nice family of sentences eta I such that you can specify for which of them quantifier blocks will behave nicely and for which don't. You can precisely make it, for example, you can make omega or any other set definable in this way. You can have a model in which no non-standard disjunctions are true. So you can make those kinds of pathologies. So there was a hope that maybe we could construct a class that satisfied propositional soundness, not by virtue of being very correct, but being very pathological. So all tautologies are true. but that's only because every sentence which has many conclusions is false. So only sentences that have few conclusions, including tautologies, can be true. But then, saturation result also blocks this approach. You cannot really manually construct satisfaction classes when you have something like Lachlan in your way. The same way as Lachlan's theorem says that there has to be some substance to the proof of conservativity of CT minus, this theorem says there has to be some substance to the proof, some more substance to the proof of conservativity of propositional soundness. Loose remarks for the ending. The result itself doesn't prove that this is not conservative, because as Roman already noted, the result follows just by saturation. But this is a finite theory, and it kind of entails its own saturation. It kind of entails its own overspeed. So can you do it in a finite way without essentially having induction? So my hope is no, but I don't have any firm reason for this. But I think of some kind of smallest, very small Fisher-like principles. Maybe there is some meta theorem in our range which will prove it. As I said, this kind of induction we obtain does not entail delta zero induction in general, but in case of CT minus, it does. The induction over sequences, over coded sequences. So in general, this seems to be a growing body of results that propositional soundness has to be equivalent to global reflection, but this is a very vague remark, because of course, this is not a theorem in this talk. Okay, thank you for your attention. Sorry for going slightly past the time, I think, and for going quite quick at moments.
You're exactly on time. Yeah, so let's thank our speaker. This was very good.
Where is this now?
Yeah.
Yeah.
I'll open it up for questions. Okay, I'll go then. Can you go back a couple of slides? I think it was about this. Yeah. Sorry. No, one more. The previous slide, 14. Yeah, here. So this was Roman's question about do we have a sense of how high this C must go, and
or maybe how low can it go?
Yeah, so I guess that's maybe my question is, does this entail some sort of induction up until C? Does it
Induction up until
entail
C.
like delta zero induction, but only if you cut off
Yes, it
C
does.
up until C or something?
Exactly. Yes.
Yeah,
Yes.
okay.
It's not trivial, but it does. It follows from the disjunctive correctness paper. There is a proof there that all the different different in the general case forms of induction are actually equivalent for truth predicates.
Okay.
But then again, like delta zero induction up to some non-standard C is something that can be arranged just from saturation. Again.
Yeah.
So
but this induction up to C seems interesting. This was
it's like the piecewise coded, like it's a class, but up to a certain
right.
Or the truth predicate is a class up to a certain part. But yeah.
And I would be very happy to know, whether you can say anything about the C. So my hope is that, like that, since there is no reason why any specific C would work, that any C would work, which means that simply induction holds. So that's my hope, and I hope that there might be some, like meta-theoretic result in the range that would show that you just cannot have this kind of blank induction up to point C, because no C has any privileged reason to end up being this induction, especially across all models, right? So,
Other questions?
Yeah, by the way, sorry, I know that the stock, I was kind of think that the stock might be a bit too technical, but I think it's, like, it's kind of annoying because it's kind of, I think, says something about the result, but in a way that might require some buy-in into the problem. So I'm very sorry if.
If you can you go back to the proof of the non-uniform version?
I think there was some question, like someone.
Okay. Oh yeah. So yeah. Right here. So okay. I'll buy express sometimes the five households. Okay. Next slide, please. Yeah. It was there. This was where I couldn't keep up in my notes, but I just want to read it for a second. Let's see. Okay. I need to go back and understand this notion of the disjunctions with stopping conditions to probably make sense of this. So maybe I'll bug you over email if
Yeah, we're
if I
very
can't make
happy to be
sense.
back.
Are there other questions?
Yeah.
Oh,
Would you be able
okay,
to go back to the slide near the beginning with the different notions that all ended up leading to general reflection?
Yes. So yeah, so this is not a complete list by far,
Right.
but
You mentioned that they're all proved in very different methodologies. Could that tell us something about what all these different notions would mean in other contexts and how we might be able to prove things in other places regarding if these things end up lining up somewhere else?
Well, of course, this is a very broad question. Well, so of course, of course, the context here is rather specific. We're really dealing with something that looks like formally sentences. My hope was that something that looks like predicate is rather overarching and logic method for showing that one theory is stronger than another.
Right.
So we're analyzing just the, like, in a way, we're analyzing just the smallest possible reason why a theory can be stronger than another. So my hope would be that ultimately this could pop up in other contexts where you want to analyze theories so that one is essentially stronger than other, but just by tiny bit. So in all kinds of considerations, when you look at the operators that somehow jump in some kind of strength, or in set theoretic context, for example, when you care about some, for example, fine structural distinctions of whether one model is stronger than another, I think this kind of consideration can pop up. So here it's sort of, the setup is sort of specific, but the context where I think this could be used in general, this kind of research is precisely this. When you have two theories, one is stronger than the other, but only by a tiny bit. So for example, reverse mathematics, maybe some kind of analysis of operators, maybe some kind of fine structural considerations in set theory. This is, of course, the original context was philosophy. It was about discussion of deflationism. It arose in the context of the argument. So if you say truth, predicate, it's just there by stipulation, by setting Tarski, by conditionals. So how can you say it proves something? It proves new arithmetical statements. How can I just predicate added by stipulation teach us something about the world? So the answer was no. The predicate added by stipulation doesn't, but predicate added stipulation together with the induction for the predicate does. But then another answer was, but look, actually you have all these principles, all of them solve new polynomial equations. So if you say that this is not part of your concept of truth, then, like, it starts to sound like the argument starts to sound like a bit contrived. You cannot just relegate your problems to induction, right? So this was the original context.
Thank you.
Right, but my comment about those philosophical questions is that induction should be assumed about the satisfaction predicate. That's a natural. Satisfaction is defined by induction. So anyway, but there's a different discussion. It's somewhat philosophical discussions. I don't want to get into it. But the other thing, sort of what Jacob was asking. So the CT minus is an extension of PA. But what if you just take I sigma 1, say, or I delta 0 plus x? Are these
over I delta 0 plus I was more worried that we'll ask about set theory because over set theory there are some slight differences which should be cleaned up in a paper, and someday we should probably just sit down and write it, because there might be slight difference, but like the gist of it is that essentially over any reasonable enough theory, this will hold. Like especially if you, in particular, if you go to subsystems of PA, then this should just like above delta 0 induction, let's say, not very big subsystems, but this should just hold. So in this context, I was thinking maybe that the question was a bit more general. If you just ask whether this is only for PA, no, this is not like specifically PA. This is general.
No, but it would be nice to have a result that's about PA only, because I really like those results which show that PA is somewhat necessary for certain kind of model theory. But there are very few of those.
This phenomenon doesn't seem to us to really. Well, like there's a bit of longer discussion because many of these, actually there are some equivalents which I could put here, but many of these things actually prove PA already. So if you say truth CT minus plus I sigma 1, so in a way it is about PA. So if you say I sigma 1 plus CT minus, or I delta 0 plus x plus CT minus plus propositional reflection, since global reflection follows, this is global reflection for PA, so get PA in particular, right? So if you they hold in the sense that if you start from much weaker theories, the equivalence will still hold over weaker theories, but the theories themselves will explode all the way up to PA. In a way, like it's very similar to Kreisel's result, right? That if you take reflection over weak arithmetical systems, you end up with PA, right?
Any other questions? Okay, let's thank our speaker again, and then I'll stop the recording. So thank you, Bartek.
Thank you, Bartek.
Thank you.
It was a pleasure to be here.
Next week, I believe we have Zach Mackenzie will be speaking so at the same time. So let's come back. I have to double check what the title is. It should be online now.